Hi, and thanks for coming to my AIChE pre-recorded talk. And I'd like to thank the organizers for inviting me to the session. Today, I'll give you a brief overview of some of the work done in my group in recent years in accelerating the machine learning and data-driven and high-throughput discovery of new open-shell transition metal complexes and catalysts. If you'd like to learn more, please check out some of the talks you can find on YouTube that are in a more extended format from my group, as well as the ones linked to on this poster. So to give you a brief overview of what my group works on, we have pioneered the development of data-driven models for the accelerated discovery of transition metal complexes. And transition metal complexes are complex materials where the amount of chemical space we could explore is really large because there are more tunable knobs than in other simple materials. We have to think about questions of magnetic ordering and spin state, as well as possible accessible oxidation states. And as a result, the challenges we would think about for building data-driven models are distinct. And so in particular, when we first got into this about 4 years ago, we thought about what are our wish list for first properties we'd like to build. My group develops a open source code called MolSimplify. And so what we wanted to do was develop a geometry-free representation that could predict important properties to transition metal chemistry, including the ground state spin and spin splitting between those two states. And because we were going to be training on DFT data, we wanted to do this with awareness of how sensitive any prediction was to the underlying DFT functional we had chosen for this prediction, as well as other related properties. Once we got this working, it worked just as well for redox, catalysis, frontier orbitals, and so on. And so we worked with relatively modest data sets because the molecules I'm showing you are large, and some of the challenges for just getting a single point for our data set size would take days. And so we tend to work with relatively modest data sets as opposed to the ones in organic chemistry where people could routinely generate hundreds of thousands of complexes. We work more on the scale of around 1,000 data points, and we work with mononuclear octahedral transition metal complexes in multiple spin and oxidation states. And we first addressed the challenge of overcoming the sensitivity to the exchange correlation functional by training our models on a family of functionals. And where we really dedicated our first efforts was in thinking about these questions of representation. So what was done commonly at the time was thinking about representing all of the atoms to the model, just like we do in a computational chemistry calculation. But we also know in open shell transition metal chemistry that heuristics such as ligand field theory that throw away almost all information except about what's directly bonded to the metal tend to work really well. So we knew the right answer was somewhere in the middle, and this matters when you're thinking about building data-driven models on the scale of 1,000 points. In the limit of infinite data, tailoring the representation matters less. And so when we did this two ways. The first way we did this was fairly ad hoc. We just developed a series of ad hoc features such as metal, coordinating atom, bond order, differences in electronegativity, and we dug into the drug discovery literature and found things like the truncated Kehr shape index. And this really was a back and forth with me and my student where we would try a descriptor we thought would work, and we would try them, and if they worked in regularized linear regression, lasso, then we kept them, and so on. And we retrospectively call this MCDL25. It was a sparse metal-centered descriptor set. But there are other things you might think about that are much more non-local in nature. So this is a descriptor set where we really baked in what we thought was most important, whereas there are other properties such as atomization energy where you might care more about how many atoms you have in the system, and you could ask yourself, well, how do we bridge this gap and how do we be more systematic? The way we did this was we extended something called Moreau-Brodo or autocorrelation functions, which are products on the molecular graph, and we adjusted their scope. We introduced differences, and these are only on the molecular graph, so they don't include explicit 3D information, but we added ligand-centered and metal-centered products and differences of heuristic properties, and these are nuclear charge, electronegativity, covalent radius topology, and identity. And these racks, as we call them, can be mapped exactly back to MCDL25 like heuristics. So for instance, the metals identity or coordinating atom identity are the zero depth ligand centered or metal centered Z racks. Our electronegativity differences are the one-depth LC, ChIRAC, and so on. And so when I show you some of the maps of these racks, one thing that we can do is we can aid interpretability of our models by pulling out the most important racks to predict a feature. And so when I do that, I will call the nuclear charge and electronegativity more electronic in nature, covalent radius topology and identity more geometric in nature. The other thing we can do is we can distinguish how far away information is encoded from the metal center, and we'll call ones that only use information close to the metal center proximal and the ones far away distal. And so principal component analysis shows us why it's important to think about building metal local descriptors like the MCDL25 one that I showed you. So in both cases, we're looking at a whole molecule featurization and the principal component analysis. And we can see that what it's doing is doing a really good job of clustering molecules by size. But differently sized molecules in transition metal chemistry can have very similar properties. And so if we instead look at one of our local representations like MCDL25 that we developed, the model has to work less hard to figure out that these two molecules that are very different in size have very similar properties. And as a result, on the same data set size, we reduced our errors on our models by more than an order of magnitude. And as a result, even on small training sets, MCDL25 could be quite predictive, predicting correctly over 97% of DFT ground states and getting error with respect to DFT down to around 2.5 kilocal per mole mean absolute error. Now, actually, our systematic RACS feature sets did even better, getting to sub-kilocal per mole accuracy. You might think that's just because RACs are higher dimensional, but when we carry out feature selection, either on just spin splitting, let's say, or on a range of features, we get down to the similar dimensionality of MCDL25. And so you might be wondering what is different about MCDL25 versus our RACS feature subsets. Well, we can color these features by proximal, middle, and distal. And if we do that, we just repeat what I told you earlier, is that MCDL25 encodes a lot of metal-centered information and throws away most of the non-local information about atoms far away from the metal. RAC 155, the full feature set of all RACs, by definition, because it includes this increasing expansion, there are many more racks that encode non-local information. And when we apply feature selection, say on the universal URAC 26 feature set, you can see we get back to a heavy emphasis on the metal center. However, where URAC 26 differs from MCDL25 and why it does better than MCDL25 is in how the mid-range information is encoded. And so that's the difference between what we were able to do from intuition versus what we were able to do with systematic feature selection, is that the mid-range information was a place where we lacked creativity. We just didn't know how to encode it. And as a result, models that were developed systematically could more accurately encode those effects. And once we had these models, we could do neat things with them. We have a structure generation code called MolSimplify. We could actually use MolSimplify in a divide and conquer way, where we let force fields work for the organic parts, and then the metal ligand bond, which is something like even the universal force field can fail to predict. We instead use our neural net to actually predict the metal ligand bond length, because we don't encode any information about the geometry. And if you'd like to try this out, I encourage you to check out our website, where some of my students, Naveen Arunachalam and my postdoc, Michael Taylor, as well as a number of other students in my group, have been working on putting online our code, which is also available at the command line. So you can now test out our neural net, as well as test out structure generation, download structures, and take a look at getting spin splitting and other properties, as well as where they are with respect to the training data that went into the model, in seconds rather than the hours or days that doing full DFT calculations would require. So beyond just faster property predictions, it's essential to understand that we can actually, at this point, start to think about getting rich insight into why materials behave the way they do, so we can start to think about designing atom by atom. And so what I'm looking at here is a porphyrin, and these are all properties that we've predicted with neural nets, but we use random forest to rank feature importance and then usually post-process it with recursive feature addition, say in a KRR model. But interchangeably, RACs can be used across a range of models. And here what I'm looking at is the ranked feature importance. And I'm going to color different atoms blue if electronic features have higher importance, yellow if geometric features have higher importance. I'm going to make an atom big if it's important to the prediction, and I'm going to make it small if it's unimportant. And so this is a larger spin splitting set, but this one over here on the right is URAC26. It's a smaller subset of the spin splitting set. And what you see is that both of these are showing us that ligand field theory in fact works. If we want to predict the spin state of one of these complexes, we should know a lot about the metal and the direct coordinating environment, especially the electronic properties of those atoms, and the atoms further away are a lot less important. But where it gets interesting is where we contrast this picture to other properties. So if we look at what it takes to predict the metal ligand bond length, all over the molecule lights up much more evenly and also much more balanced between electronic and geometric properties. Then redox lights up an entirely different part of the molecule with a heavy emphasis on geometric properties. And so now this gives us a path to completely orthogonal design of redox and spin splitting properties. And this idea can be readily extended to understanding differences in GCMC predicted gas absorption properties of methane versus CO2 and metal organic frameworks, as we recently shown in the paper on the left. It can be extended to understanding why catalyst heuristics, such as the frontier orbital prediction of catalytic activity, will work or won't. In models of understanding what determines the formation of metal oxo intermediates in single site catalysis. But I'd like to finish by telling you a little bit about where I think this is going. And so in particular, where machine learning accelerated materials discovery is most poised to make an impact is in addressing complicated, messy real-world challenges where multiple objectives have to be satisfied. And so we took a look at this first in redox flow battery, redox couple design. Transition metal complexes are common redox couples used in these materials. Vanadium AIChE is one of the most famous ones. And in order to design a new material, we need something that's stable, resistant to crossover, has good solubility in polar non-aqueous electrolytes, and has a high redox potential. And so we address the question of stability and resistance to crossover by building and enumerating a very large pool of candidate materials from experimentally motivated heterocycles that would create bulky complexes resistant to crossover. And as a result, we ended up with around 2.8 million complexes that range from 100 to 200 atoms in size. These would be very computationally demanding to carry out DFT calculations on, and they're not like anything we'd ever studied before. So we had really no idea what the best molecule was going to be in this space. And then we used an approach known as efficient global optimization with the 2D expected improvement criterion to simultaneously optimize solubility and redox potential. And what we do is we start in a cartoon I'm showing you here. We start with some DFT data. We train the neural net, and based on a few points, we ask the neural net, what do you think of these 2.8 million complexes? And what we're looking to do is move past the Pareto front. So we ask the neural net which points are, with knowledge of the neural net uncertainty, most likely to go past those points. We then pick those out to study. The model may or may not be correct about them, and then we use that to retrain a model and repeat this process. So this is what it looks like in practice. We spent about 2 weeks with DFT, and this is how many points we got. And then we went over to the neural net for about 3 minutes, asked it what it thought of 2.8 million complexes. This is the Pareto front here. We looked for points that would move past the Pareto front, and you can see we went back to DFT, and after about a week, things didn't look too much better because the model wasn't very predictive yet over the whole space. But if we repeated this a number of times, the model starts to get smarter, but it also starts to get pessimistic that it can really do better than the best complexes we've ever seen. So after about 6 weeks with DFT, we decided we were finished, and about 15 minutes with the ANN. And what you can see is that all of the Pareto front points are from the last generations of this model. They also have convergent key properties. The main thing is the best design principle we ended up with was manganese high spin complexes with oxygen coordinating atoms and sulfur in the ring, as well as small polar groups to help increase solubility without reducing redox potential. And if you compare this to what we could have done through random brute force search, we got at least 500-fold acceleration over already parallelized high throughput GPU accelerated quantum chemistry. And this doesn't sound very impressive until you realize it's the difference between having an answer in about a month's time versus not having an answer in your lifetime. And so we believe this is a really powerful approach. It's multiplicative in nature. So more objectives to satisfy, things about catalysis activity, stability, cost, earth abundance are where my group is headed now. And I'd just like to finish by acknowledging the funding sources, as well as the members of the group who did the work. This work was pioneered by John Paul Janae and Timmy Anidis in my group. And I had the pleasure of showing you contributions today from Chen Rujwan, Aditya Nandi, Michael Taylor, Naveen Arun Shalom, and Daniel Harper. Thank you very much for your attention.